The research paper introduces a novel framework for uncertainty quantification in Data Shapley, a method used to value data points based on their contribution to model performance. It establishes a connection between Data Shapley and infinite-order statistics, enabling the analysis of uncertainty introduced by data variations. The authors propose two algorithms for uncertainty estimation and conduct experiments to verify asymptotic normality. This work aims to enhance data valuation by providing confidence intervals for estimations and facilitating more accurate data trading. The framework addresses limitations of traditional Data Shapley by considering dynamic data environments. The authors contribute to the development of adaptable and trustworthy data valuation methods, bridging the gap between static and dynamic data scenarios. The research paper discusses the concept of Data Shapley, a method derived from cooperative game theory for quantifying the contribution of individual data points to a model's performance. It introduces the Data Shapley distribution, establishing the asymptotic normality of the Data Shapley estimator and providing tractable formulas for uncertainty quantification. The paper also proposes two algorithms for estimating the asymptotic variance of the Data Shapley estimator. The relationship between Data Shapley and infinite-order statistics is explored, highlighting the connection through the definition of new S, Z, B. The distributional Shapley value is introduced, focusing on enhancing the robustness of data valuation against dataset variations. The paper concludes by noting the computational challenges and proposing a Monte Carlo approximation for new S, Z, B. Throughout, the work emphasizes the importance of asymptotic analysis in data valuation, providing a credible valuation interval as data volume approaches infinity. The research paper focuses on establishing the asymptotic normality of Data Shapley, a crucial concept in data valuation that quantifies the contribution of individual data points to model performance. It introduces a new parameter gamma, which is essential for establishing this normality and facilitates the construction of confidence intervals and hypothesis testing. The authors define the Data Shapley and its corresponding statistic, emphasizing their relationship with the utility function in deletion stability, a widely used assumption in the data valuation literature. The variance term is defined as a key component in analyzing asymptotic normality, and a theorem is presented stating that the estimated value of Data Shapley follows a limit normal distribution under specific conditions. This result expands on prior work regarding the variance of incomplete IOUS and its asymptotic normality. The paper also discusses the statistical inference procedure for Data Shapley, outlining steps such as estimation of Data Shapley using various Monte Carlo methods, construction of confidence intervals, hypothesis formulation, statistical testing, and interpretation of results. These steps provide insights into the reliability and robustness of Data Shapley estimates, enabling researchers to determine the difficulty of calculating data values, anticipate changes in data value with replacements, and assess the credibility of sellers' data valuations. Two algorithms for estimating the variance are proposed, enhancing the practical applicability of this approach. The paper concludes by bridging the gap between complex research and concise, informative summaries for expert audiences, providing valuable insights into data valuation and credibility assessments. The double Monte Carlo method and the pick and freeze estimator are two approaches used to estimate zeta 1, S, Z. The double Monte Carlo involves two layers of Monte Carlo simulations, making it computationally intensive, whereas the pick and freeze estimator simplifies the process by leveraging Lemma 6.1, reducing computational complexity. The research paper also focuses on data valuation using Data Shapley estimates, demonstrating their asymptotic normality and comparing the direct Monte Carlo and progressive fitting algorithms. The authors show how the distribution of Data Shapley estimates approaches normality with increasing sample size and highlight the trade-off between accuracy and computational time for the algorithms. They also present the process and results of hypothesis testing for data valuation using real-world data, including confidence intervals, and propose a scenario for data trading. The methods are validated using datasets such as CoverType and FashionMNIST, demonstrating their applicability across various data sizes. The research paper discusses the application of Data Shapley values in various aspects, including data valuation, uncertainty quantification, and data addition tasks. It begins by presenting empirical coverage probabilities for estimated Data Shapley values across different data volumes, demonstrating the proportion of sample data values falling within their intervals. The paper then delves into the comparison of two algorithms, DMC and PF, for estimating zeta-1, S, showing that DMC offers higher accuracy at the cost of longer runtime. A new method for data addition tasks is proposed, leveraging the 3 sigma rule to quantify uncertainty and estimate data value. Experimental results on the fashion MNIST and cover-type datasets demonstrate the effectiveness of this approach, outperforming other methods in data addition tasks. The paper also presents a comparative analysis of Data Shapley and random data valuation methods in data addition tasks, highlighting the importance of considering variability in data value estimation. The transaction process dependent on confidence intervals is explored, involving the seller providing data points, the buyer assessing credibility by calculating value and confidence interval, and making a decision to proceed with the trade based on these calculations. The research paper explores the concept of Data Shapley, a method for valuing data in machine learning from the perspective of statistics. It derives the asymptotic normality of Data Shapley's estimated values, enabling statistical inference and confidence interval estimation for data value estimation. The authors propose 2 methods for estimating limiting variance and discuss their applicability. Simulations on real datasets demonstrate the effectiveness of Data Shapley in estimating data values. The paper concludes by discussing practical applications in enhancing the credibility of data valuation, aiming to extend these valuations to more real-world trading scenarios. The author's contribution lies in developing a robust method for data valuation, increasing trust and credibility in data trading markets. The paper draws upon a comprehensive range of prior works in data valuation, machine learning, and statistics, citing numerous seminal papers and authors. The authors provide a detailed proof for the Lindbergh condition and Theorem 5.1 in the appendix. They begin by stating Lemma 8.1, which controls the predicted tail behavior under specific conditions on the function hs. This leads to the conclusion of Theorem 5.1 through the application of Hoeffding's inequality and the Kramer-Rao lower bound inequality. The probability of h1 s z exceeding a certain threshold is shown to decay exponentially with respect to n, thus satisfying the Lindbergh condition. To prove Theorem 5.1, the authors define the Hayek projection of nu s z n ms minus nu s z. By utilizing the linearity of expectation and the fact that subsamples are selected uniformly at random with replacement, this projection can be rewritten in terms of a binomial distribution. Ultimately, the Hayek projection equals S, n1, times a sum of h1, s, z terms, a crucial step in the proof of Theorem 5.1. A triangular array involving the functions h1, s, z, and combinations of S distinct elements from Z1, Zn, Z is also defined, playing a pivotal role in the subsequent analysis. The authors calculate the expected value and variance for each variable in the array, leading to the satisfaction of the Lindbergh condition. Applying the Lindbergh-Feller central limit theorem, it is demonstrated that the sum of variables follows a standard normal distribution. The limiting variance ratio of the incomplete statistic and its projection is compared, utilizing the relationship established by Blom, 1976. This ratio converges to 1, indicating equivalence. Finally, Slutsky's theorem and van der Vaart's theorem 11.2 are applied to show that the difference between the incomplete statistic and its projection, along with the projection itself, converges to a standard normal distribution. This series of mathematical derivations and applications of theorems culminates in a comprehensive understanding of the statistical properties of the incomplete statistic, particularly its convergence to a standard normal distribution under certain conditions. The proof of Theorem 5.2 is presented, involving the application of the Lindbergh-Feller central limit theorem. To satisfy the theorem's conditions, the variance of the sum of random variables is shown to converge to a finite limit, and the Lindbergh condition is satisfied. The variance is given by 1 n gamma squared sum underscore s equals 0 caret n gamma 1 s squared zeta underscore 1 s z, which converges to a finite limit as n to infty. The Lindbergh condition holds, as the probability of the absolute value of the standardized sum exceeding any positive value, epsilon, tends to 0 as n to infty. The second part of the theorem is proven by bounding the difference between the variance of the sample mean and the variance of the population mean. This difference is shown to be of order O sqrt n caret 1 nn gamma log n gamma plus 1 n gamma caret 3 halves and O sqrt n caret 1 log n gamma n gamma caret 3 halves, both of which tend to 0 as n to infty when gamma geq 1/3. Slutsky's theorem is then used to combine the results, yielding the overall result of the theorem sqrt n hat nu z n gamma m nu z n stackrel d to n 0 1. Empirical validation of the theoretical findings is provided across various datasets, as detailed in Table 3. The application of double Monte Carlo and Pathfinder algorithms in estimating the value of a given data point is explored, with a focus on the normality of these values across multiple datasets. Experimental results demonstrate the normality of the estimated values, strong correlation between theoretical and sample quantiles, and nearly 100% empirical coverage probabilities. The runtime and accuracy comparison between DMC and PF algorithms on the fashion-MNIST dataset is presented, highlighting the trade-off between accuracy and runtime. The study contributes to the understanding of statistical inference in machine learning and the development of efficient algorithms for data analysis. The analysis of estimated values for phoneme, vehicle, and wind datasets with a training set size of 100 and gamma equals 2/3 is presented in Figure 10. The first column displays the confidence interval graphs for the datasets, illustrating the accuracy and precision of the estimates. The second column provides the QQ plots for the estimated values, which demonstrate that the observed quantiles closely follow the theoretical quantiles, indicating a good fit between the model's predictions and actual outcomes. The third column depicts the empirical coverage probabilities, confirming almost 100% coverage, suggesting that the model's confidence intervals are well calibrated. In Figure 11, a comparison between the DMC and PF algorithms on the fashion-MNIST dataset is provided. The left panel, Figure 11a, shows the runtime comparison, with t equals 100 for both algorithms and varying inner loop counts for DMC. The running time of DMC increases rapidly with the number of inner loops, far exceeding that of PF. This indicates that while DMC may provide more accurate estimates, it is computationally less efficient than PF. The right panel, Figure 11b, shows the estimated values of zeta 1 s using DMC with varying t. As t increases, the estimated values become more stable and accurate, suggesting that increasing the number of iterations improves the precision of the estimates. This highlights the trade-off between computational efficiency and accuracy in the context of DMC and PF algorithms.